Next up is devising and balancing half reactions. So sometimes what you'll see is questions will give you an incomplete half reaction. They won't give it to you as a balanced half reaction. Now sometimes we've seen half reactions come out of the booklet. What you need to understand is out of this booklet, in your data booklet, this chart, this reduction half reaction table is not complete. It doesn't contain every half reaction that's out there. And so what we have to be able to do is, if they give us certain substances that turn into another substance, we have to be able to identify by devising these half reactions whether it's a reduction or whether it's an oxidation, and then be able to balance those half reactions out. So I'm going to show you how to do that. Here are the rules for doing it. The first thing that we're going to do is we're going to balance the atoms that are not oxygen and hydrogen. So we'll come over here to the first example and we'll just go ahead and do that. So if we take a look at this, we can see that we've got some oxygen here. We're going to ignore those to start. We do have some manganese. So one manganese on this side, one manganese on that side. So that one's done. So then I move to step 2, and we do balance the oxygens next by using water molecules. So on this side I've got 4 oxygens. So on this side I need to add 4 water molecules to get 4 oxygens on this side, so that the oxygens are now balanced. Then I move to step 3, and it says balance the hydrogens using H+. This side now has 8 hydrogens on this side. 4 times 2 gives me 8. So I've got 8 hydrogens on this side, which means I'm going to add 8 H positives on this side. And then finally, the last thing that I do is I balance the charge using electrons. So the charge over here on this side of the reaction is just a sum of all the mini charges that I've got. So I add up all the positives and all the negatives, and I get a total sum of a charge on the reactant side. And I can do the same for the product side. So over here I've got 8 positives and 1 negative. That gives me a total of +7 on this side of the reaction. Over here I've got 2 positives plus 0 for water molecules that are all neutral. That's just equals 0. And so that equals a +2 altogether on that side. So now what I'm doing is, to balance the charge out, I'm using negative charges. I'm using electrons. So there is only one side that I can add electrons to that's going to balance this out. If I add it to the wrong side, then it's going to actually take the charges further away. So if I add, for example, negatives to this side, this positive 2 is going to become more negative, becoming further away from the +7. So I don't want to add it to this side. For this one, I need to add it to the reactant side. And if I add 5 electrons here, and then change my math so that now instead of 1 negative, I've got 6 negatives, you can see now that this turns into a +2, which then balances out with the charge on the product side. And that reaction is now balanced. If you take a look, that reaction is actually, in fact, in your data booklet, and you can see it as the third one from the top, and you can see that it matches perfectly with what we have on the board. The next one here, if we take a look at this, again, following the rules, balancing the atoms except for oxygen and nitrogen to begin with, or oxygen and hydrogen, sorry. In this reaction, I am going to balance the nitrogens first. I have 2 over here, and I need 2 over here, so I'm going to put a 2 on that side. Then over here, I'm going to look at my oxygens. I've got 4 oxygens, so I'm going to put 3 waters on this side. The reason I put 3 is because I already have 1 oxygen over here to accumulate up to 4, so that's balanced. Now I look at my hydrogens. I've got 6 on this side, and I have 2 on this side, which means I only need to add 4 more H pluses. And then finally, tally up the charges again. On this side, I have a total of +4. On this side, I have a total of 0. And so I'm going to add 4 electrons to this side to balance this out, so that both sides have the same charge. Something to point out is, as we've gone through the various concepts throughout this unit, if you take a look at all of the balanced redox reactions that we've looked at, or all of the balanced half reactions that we've looked at, you'll notice that the charge for each of those reactions is always balanced on either side of the arrow. And so a way for you to check your work to see if you've done things correctly is if the charge is not balanced, you know you've made a mistake somewhere. And it's not a foolproof way to identify every mistake, but it does help you identify some mistakes if they do exist. So checking the charge to make sure that the charge is the same on both the product and the reactant side is a good idea when checking your work. So a little bit more on devising and balancing half reactions. Sometimes what you'll see is instead of an individual half reaction that you have to balance, they'll give you a full redox reaction that's not balanced. And so you have to break it up into its two individual half reactions and balance those using these rules. Now, something that you can do as well is you can assign oxidation numbers to these and to each of these compounds in this unbalanced half reaction or unbalanced redox reaction, and you could identify what is your oxidizing agent and what is your reducing agent. For this video, I'm not going to do that. If you want to revisit how to assign oxidation numbers, then you can go back and watch that video, and then you could come back and assign oxidation numbers to this one if you'd like, just as extra practice to identify oxidizing agents and reducing agents. So jumping into this, we can see that a chromium containing compound here is obviously going to turn into a chromium containing compound over here. So my 1/2 reaction is going to be Cr2O7, 2- aqueous, turns into Cr3 positive aqueous. My other half reaction is going to be the HNO2 turning into the NO3 minus aqueous. And so you can see my half reactions have to be grouped up with substances that are turning into other substances that are there. The dichromate ion is not going to turn into the nitrate ion. That just doesn't make sense. It's not made of those pieces, and so that's why we group it this way. So I'm going to go ahead and use these rules to balance out these two half reactions. So I'm going to balance the chromiums first, make it 2. Then I've got 7 oxygens, which means then I need 7 waters on this side. And then I'm going to balance out the charges, balance out the hydrogens. So I've got 14 hydrogens that I need over here. And then I'm going to balance out the charges. So on this side, I've got a total of +12, and on this side, I have a total of +6. So I'm going to add 6 electrons over here, and then that will give me a total of +6 on both sides. For this one right here, my nitrogens are balanced. I'm going to balance the oxygens. Next, using water, I've got 3 and 2, so I only need 1 more water over here. Then I'm going to balance my hydrogens, being careful that you're counting all the hydrogens on the whole side. So here I've got 2, plus I've got another one right here. So that's 3 hydrogens altogether. So I do it like that. Then I look at the charge on the reactant side, which is 0. And the charge on the product side, which is +3 plus a -1, gives me 2, +2 altogether. So if I add 2 electrons over here, then that should balance it out. Okay, so now I've gotten this far and we've done this devising and balancing half reactions. What I can do now is, because this is an unbalanced redox reaction, I can add these two up together by balancing the electrons out, and I can get a balanced redox reaction. So we've done this skill before, but just to revisit, I've got 6 electrons here and 2 over here, so I'm going to times this reaction by 3 to get 6 electrons so that those can cancel out. So times this by 3, 3, 3, this is a 9, and that becomes a 6. Now my electrons cancel. And a few other things cancel out as well. You'll notice that I've got 3 waters over here. Those 3 waters are going to cancel out with 3 of the 7 waters that I have. So I'm going to have 4 left over. And then same thing with the hydrogens, the H pluses. I've got those 9. Those 9 are going to cancel out 9 of those 14, leaving me with 5 left over. So once I've done that, then I can add up everything that's left over in that reaction and write out my balanced reaction. So I've got 5H plus aqueous plus 3H NO2 aqueous Cr2O7 2 minus aqueous turns into 2Cr3 positive aqueous 3NO3 minus aqueous and 4 water. And that's my balanced redox reaction here from my unbalanced redox reaction that I started with up above. Here's one more example that I wanted to go through with you because it's a little bit different. Again, this is an unbalanced redox reaction. There is an oxidizing agent and a reducing agent here. And I'll write out what the two half reactions are. What you'll notice here is that I only have one reactant for this. And this one reactant turns into 2 other things. I'm not going to balance these 2 half reactions out for you. You can do those on your own if you want to pause the video right now. What I'm going to talk about moving forward is what does this mean in terms of oxidizing agents and reducing agents for this reaction. So to explain this, I'm going to assign some oxidation numbers to these. So first of all, I know that oxygen is a -2. That makes this bismuth a +1. Over here, again -2. That gives a total of -6, so this is a +5. And this bismuth is an element, so it's just 0. So what you can see is this bismuth here turns into that one and that one. If you take a look at the oxidation numbers, you can see that this oxidation number goes from +1 to +5. That means that this substance was oxidized. But if you take a look, also it goes from +1 to 0, which means that it gained electrons. And so this substance here actually undergoes oxidation and reduction simultaneously. And when a substance does that, when we have a substance that undergoes an oxidation and a reduction at the same time, we call that a disproportionation. And that's just a term that you need to know and its definition. This is still a redox reaction, but it is a type of redox reaction that we call a disproportionation, in that a substance that acts as both the oxidizing agent and the reducing agent in the reaction can still undergo and make products, but it's acting as both. So one last concept as it relates to devising and balancing half reactions. We've got one last piece to these half reactions that we need to understand. So if you turn in page 7 in your data booklets to this reduction half reaction table, what you've probably noticed as we've been working through this information is you can see that down the right hand side we have these numbers that are in units of volts. And so you can see some of them are positive and some of them are negative. What this is referred to as is electrical potentials. And an electrical potential is just describing the ability that a substance has to either gain or lose electrons. So because we have two half reactions, there's two types of electrical potentials. For reduction half reactions, we have reduction potentials. And for oxidation half reactions, we have oxidation potentials. Now in this booklet here in this table, this chart is a reduction half reaction table. So naturally, all of these numbers down the right-hand side are all reduction potentials. So what this means is that this shows the ability that these half reactions have to gain electrons. Now, if I write these reactions backwards from how they're written in the booklet, that will give me an oxidation half reaction. And so if I'm going to write its corresponding electrical potential with that, I have to flip the sign of the sign that's written in the book here. So for example, if you take a look at this half reaction, it's near the top. It's the sixth one down from the seventh one down from the top. And it's right here. You can see if you look all the way across, its electrical potential is positive 1.30 volts. And I've written that down over here on the side, positive 1.30 volts. And that's because this is a reduction half reaction, and that's the number that's given in the booklet, because this is a booklet or a chart of reduction half reactions. So there it is. This half reaction is written backwards as it's written in the book here, and it's because for every redox reaction, I have a reduction half reaction and an oxidation half reaction. And so because copper solid in this redox reaction is losing electrons, it's going to be written as an oxidation half reaction. But when I go to write its electrical potential, its oxidation potential, I have to write it as an oxidation potential, not a reduction potential. And so the one that's listed in the book here, if you look, you can see here's the copper 2 positive half reaction. You scroll across and you can see that this number is positive 0.34 volts. That's for the reduction of Cu2 positive. This is the oxidation of Cu solid, so the oxidation potential has to have the opposite sign. And so all a positive number means, a really high positive number, if it's a reduction potential, means that it's really good at gaining electrons. So we know fluorine is really good at gaining electrons, so it's natural that its electrical potential, its reduction electrical potential, is going to be higher than the rest. You can see here that lithium, positive, has a very, very negative electrical reduction potential, and that's because it's not very good at gaining electrons. But if you were to write this as an oxidation half reaction and flip the sign of this, you could see that its oxidation potential would be quite high, positive 3.04 volts, meaning that it's really, really good at losing electrons. So that's what these electrical potentials mean. So if I were to finish out balancing this unbalanced redox reaction that I started with, and I write out my reduction half reaction, and I write out my oxidation half reaction, and then I go ahead and I balance these electrons. So this is going to be a 2, a 2, and a 4. Then I can cancel these electrons out, and I write out my balanced reaction. And I'm going to rewrite this over here. I can do the math for that, and my electrical potential, which I just write as my E net, is going to be a positive 0.96 volts. And I got that number from these two numbers here. Now, something you may have noticed that I did or didn't do was that when I multiplied this reaction by 2 to make it so that I could cancel these electrons out, I didn't multiply the oxidation potential by 2. And kids sometimes get this confused with the energy unit that we did earlier, which was that, if I multiply this reaction, then I have to multiply the energy term by the same amount. And for electrical potentials, we don't do that. And the reason why is because electrical potentials are only a representation of the ability that a certain atom or molecule has at gaining or losing electrons. So whether I have 2 of them or 5 of them or 10 of them, they all have the same ability. And so this ability needs to be unaffected by this multiplication here that we do for this. And so that's why we leave that number alone. Make sure that you don't multiply those numbers. And then when you add all this up together, you just simply add these two numbers, gives you your net electrical potential of positive 0.96 volts. One last thing that we learn from these electrical potentials is that if the net electrical potential for a particular redox reaction is positive, then that tells me that that's a spontaneous reaction. If it's a negative number, then that tells me that it's a non-spontaneous reaction. So for this reaction here, because it's positive, this is a spontaneous reaction.